Hey there, Calc 2 folks, back here with just a couple more videos left. This is, I think, the second to last video I have for you. Now, what happened here? Get that back up in the third dimensions, right? Where in this video, as you can note here, we are going to continue our study of vectors, where we point out in this section of material that vectors can be used to define what we say are lines and planes in three-dimensional space, right? We're going to be kind of continuing on into venturing out into our different dimensions of space by moving out into the third dimension and considering how would we define a straight line in three-dimensional space, and then how do we start to define some of the first surfaces we encounter in three-dimensional space, known as planes or a planar surface. And the way that we're going to go about defining planes and defining lines, straight lines in three-dimensional space, is by using some vectors, right? And in fact, what we're going to find is to denote any curve in n-dimensional space and beyond the dimension of two dimensions, we're going to have to rely on a parametric description of that curve. We are going to have to rely on what is going to develop back into when you return to Calc 3 is the idea of a vector valued function, or what is a parametric description of a curve expressed in the context of a vector. This is all going to be what we come back to at the beginning of Calc 3. But here in this section is where we are first introduced to some of those ideas of vector-valued functions. That being, how do we describe a line, a straight line in three-dimensional space, and then move into how do we start to describe surfaces, right, in an n-dimensional space, in a three-dimensional space, for instance. We are introduced to some of that with the idea of planes here. All right, but as noted, vectors are going to play a role, right? And we see that in the definition, first of all, for the line here, right? By definition, a line in three-dimensional space with coordinates described by the x, y, z coordinates in that space. In the direction, right, if that line is described by the direction v bar equal to a, b, c, and passes through an xyz coordinate at x null, y null, z null, right? It's described by xyz in the plane, right? We'll go ahead and bring this down. It's described by what we call a vector equation, right? Or what we might refer to as a vector equation or a vector function of, right, r equal to r bar of t, for what we would say is some parameter at t. And that would be where this vector function, right, that would describe this line in space would be given by the vector describing the location x null, y null, z null, right, that coordinate in our plane with respect to the origin, added to the parameter t times the vector ABC, which is the vector describing the direction of this line. And if we expand, right, the summation of these two vectors, where the second summation is really a scalar product of the parameter t with the vector ABC, we do end up with this result, this vector description in three-dimensional space given by x null plus at, y null plus bt, and z null plus ct. This, folks, is the beginnings of what we're going to define as a vector-valued function. The beginnings of what we're going to be coming back to in the early days of Calculus 3, right? Where we're going to be looking at expressing a line in three-dimensional space or a curve in three-dimensional space using a vector description that acts a lot like a function for this parameter, right? That we're going to use the parameter of t. All right. But what we do have here, we just point out, is note this vector equation, right, or function, right, represents really just a set of parametric equations given by this three-dimensional set, where x equals x null plus a of t, y equals y null plus b of t, and z equals z null plus c of t, all for the parameter of t. And in this particular case, we might take note the entire line in R3 is going to occur over values of the parameter from negative infinity to infinity, and that coordinate x null, y null, z null that we see in this linear description of that line is going to be the location where t is equal to 0. You'll notice if you substitute t into 0 either in this set of parametrics or into this vector function, you will be just left with the location x null, y null, z null. Or if this t is made 0, you will just be left with this description of position, right? That description of position at the coordinate x null, y null, z null in the system. All right, that given point on our curve, or in this case, the given point on our line. All right, if we were to look at an example of this, let's see here, I can get this example up in the view. We might consider the line defined in three-dimensional space, right, with its direction described by the vector 4, -1, 6, and passing through the coordinate -5, 4, 0 in space, the coordinate x null, y null, z null, given by this three-dimensional coordinate, right? What we might note is the following illustration of this line, right, which also illustrates the vector describing its direction in standard position and the coordinate x null, y null, z null, right? Here is the illustration of that line, right? In this illustration, the line is the linear path we see here passing through this point. That point in our system being located at the x coordinate of -5, right? The y coordinate of 4, right? We can see that aligns with the y coordinate of 4, x coordinate of -5, and the z coordinate of 0. That's this point on our line. And what this line is doing is moving in the direction, right, of this vector, vector v, which has been placed in the standard position. Here is the center of our system. And if we place that vector v in standard position in the center of that system, it actually points off in this direction. And notice that is the direction that this line is flowing through this space, right? All we need to define this line in this space is to know what direction it moves in, which is described by the vector v bar, and to denote what point it happens to pass through, this location -4, 4, 0, -5, 4, 0 in value. All right? As for defining this line in this space, we are going to use this description of its direction and the information about this point that it is passing through. This vector description and this point that is passing through can be plugged into this formulation for the vector equation of the line, or it can be presented as this set of parametric equations, right? Where plugging in for a, b, and c, 4, -6, and 1, and substituting in for x null, y null, z null in that formula, -5, 4, and 0, right, we can prepare the following equation for this line. Right? In three-dimensional space, this line is described by, right, the vector equation r bar of t equal to 4t minus 5, 4 minus 6t, comma, t, where you can see in that equation, all we have done is substitute in for a, b, and c, 4, -6, and 1. Those are going to be scaled by t. That's where we get the 4t, the -6t, and the 1t in this calculation. And these are going to be added to the vector description of this point in space, -5, 4, 0. So 4t is added to -5, that's 4t minus 5. Negative 6t is added to this 4, which is 4 minus 6t. And then the value of t, 1t, is just added to nothing, which is just t itself. So this becomes what we call the vector value description of this line in space. And this describes the entire line, right, over values of the parameter t in this interval from negative to positive infinity. Right? Plug in any value of t into this function and you will obtain an x, y, z coordinate, a location that exists along this line. More so, we could even take note if t was 0. Notice plugging in 0 into the equation here for t, plugging in 0 here and plugging in 0 here is just going to reference the location negative 5, 4, 0 on the line. This is the point on that line where t happens to equal 0 in its vector description. Right? Now, as a set of parametric equations, right, this vector equation can actually be represented, or this vector function can be represented as this set of parametric equations where x has just been set equal to this first component, y has just been set equal to this second component, and z has just been set equal to this third component. All right? This is how we describe this three-dimensional linear path in space. All right? We need to know a little bit about what direction it heads in, and we need to have a little bit of information about where it's located in terms of a coordinate, right? And that hasn't changed with our description of lines, right? In two-dimensional space, how have we described a line? Well, we needed to know a point on that line, and we needed to know the slope of that line. Well, when you move off into three-dimensional space, there really is not a clear-cut understanding of slope. Instead, that slope gets translated to the idea of direction. Right? And that slope is, instead of being described as a rise over a run, is described as being in a certain direction in that space, where we see a change in x and a change in y with respect to some change in z. And what we notice here in this particular description of the line, x increases by 4, y will increase by negative 6, and when z increases by 1 in value, or by 1 in value, we would say, right? We see this change in our values. This, in a sense, is our description of our slope scene here, folks. All right? And thus, we can put those bits of information together about location and direction to develop this description of the line, position along that line. Right? So that's one way that vectors can be used. They are used in the description of a line, right? We use this vector v bar to give a vector value description of that line, a vector functional description of that line, which is really nothing more than an organization of a set of parametric equations into this vector description. All right? Now, we do see something similar for planes, except for in a plane, the plane is not described by a vector valued function. What it's going to end up being described is just a multivariable equation. Right? In three-dimensional space, to actually describe a surface like a plane, you're going to use a three-variable equation. And this is what we are forming in this definition. Right? A plane in three-dimensional space with coordinates described by x, y, and z, right, that forms orthogonal to the vector v bar equal to the vector description a, b, and c, and passing through the coordinate x, y, and z equal to x null, y null, and z null, is given by the following three-variable equation. That equation being what we see expressed here, where we're going to take this description of orthogonal behavior to the plane, a, b, and c, and it's going to play the role of these constant multiples, a, b, and c, on these quantities, where these quantities, x minus x null, y minus y null, and z minus z null, are just our values of the variables x, y, and z minus, right, the location for the coordinate that this plane is passing through. This is a times the quantity x minus x null being the point, the x component in the coordinate for the location of the point this plane is passing through, plus b times y minus y null being that y component of that location for the coordinate that this plane is passing through, plus c times the quantity z minus z null being the z component of that coordinate description, right? And in this equation, the variables x, the variables y, and the variable z just play the role of the variables in that equation, right? They specifically are the values of the variables that fall on the plane, that are located on this plane, that will make this equation true. You will notice as if you plug x null, y null, z null into those locations for x, y, and z, certainly subtracting x null from x null, y null from y null, and z from z null will result in 0, times these scalar factors a, b, and c will all add up to 0. And that does equal 0, right? This is a point on the plane that makes this three-dimensional equation true. And in fact, any x, y, z coordinate that happens to be on this plane will be a coordinate that makes this equation true, where a, b, and c describes the vector orthogonal to the plane, and x null, y null, and z null describe a location on the plane. Now, if you were to expand, if you were to multiply through by these constant multiples a, b, and c, right, and then it would be add all those constants to the right-hand side, you can actually rewrite this equation into a more general form, which we say is the equation ax plus by plus cz equal to d, where d is just a constant value on the right-hand side of this equation that is equivalent to the quantities a times x null plus b times y null plus c times z null, would be equivalent to this constant value given by the summation of these components, or the product of these components summed, right? We see that here in this general form, right? If we were to consider an example, right, we might consider the plane orthogonal to the vector v bar equal to 4, 2, 3, and passing through the coordinate x null, y null, z null equal to 2, 5, negative 2. Note, here is the illustration of this plane we're describing, right? It is this planar, this flat surface that exists in three-dimensional space here. It is passing through this coordinate 2, 5, negative 2, this location seen right here, where at that location I have gone ahead and positioned my orthogonal vector. This plane is orthogonal to this vector at this location, which is seen here, right? All we need to define a plane in space is to note a point on that plane, in this case this point seen right here, and some vector orthogonal to that plane, this vector seen here. With this vector orthogonal to the plane and the understanding of this location on the plane, we can define the equation for this plane being illustrated here in space. And that equation just comes from, right, substituting these descriptions for 4, 2, and 3, these descriptions for direction into the locations for A, B, and C in this formulation, and substituting these bits of information for this coordinate on our plane at x null, y null, z null into these locations in our formula for x null, y null, and z null. The variables x, y, and z will play the variable role within this multivariable equation, within this three-variable equation, right? Substituting in those values, right? Substituting in those values, we do prepare the following equation. All right? Substituting in 4, 2, and 3, our description of direction into that formula at these locations, and substituting in 2, 5, and -2 into these locations in the formula, which give us the description of location on that plane, right? I can prepare this equation for that plane where you'll notice x, y, and z are playing the roles of the variables for the equation of this plane. Right? Where if I do a little expansion, I can expand this into the statement 4x minus y plus 2y minus 10 plus 3z minus 6 equal to 0, where the statement -8 minus 10 minus 6 is all one constant value. Let's be careful here. Make sure I get this right. Yes. Sorry, this shouldn't be -6. This should actually be +6. I know that didn't seem like it added up right. This is going to be 4 times -2 is -8, 2 times -5 is -10, 3 times minus a -2, this would actually turn into +2 back here. Right, if we want to think about that. So that would result in +6 in this result seen here. Right? Where -8, -10, and +6 all add up to -12 in value, which we can move to the right-hand side of this equation by adding it to both sides. And what we prepare is this statement seen here, which is the general form of the equation for this plane. This plane is described by the equation 4x plus 2y plus 3z equals 12. Right? Any x, y, z values that make this equation true when substituted into those values is going to be a point on this plane, right? For example, I could see a point on this plane at x equal to 0, y equal to 0, and z equal to 4. Those would be 3 values of these variables that would make this equation true, would make this equal 12. So those would be a point on that plane, 0, 0, 4. All right? I could also have the coordinate 3, 0, 0. That'll make that equation true. That would be another intercept on this plane. Or I could have 0, 2, 0, which would also be an XYZ intercept on this plane. Right? And with those 3 XYZ intercepts, I could actually sketch out this plane in 3-dimensional space pretty quickly and easily begin sketching it if necessary. Right? Again, folks, we are looking at here the beginnings of surfaces in 3-dimensional space. The simplest surface we can encounter in 3-dimensional space is what we know as a plane. Right? A plane comes about from a 3-variable equation, right? That looks a lot like the 2-variable linear equations that produced a line in 2-dimensional space, but we're adding on this third linear component, which is referencing a direction in the context of z. Right? Again, this is the beginning of surfaces, folks. We want to understand they are going to be represented by multivariable equations in space. Multivariable equations do not produce lines. Multivariable equations in 3-dimensional space produce surfaces. To actually obtain a linear path, or even what we're going to find to be a curved path when we come back to Calc 3, right, we're going to need to use a vector value description of that path, right? Where for a line, we can describe a straight line in space using this vector value description, which also makes use of vectors. All right? Again, here we're seeing the beginning of just using vectors to help us define lines and planes in 3-dimensional space, folks. All right? So that is it. These ideas are not very heavy, I hope. We are looking at very simple surfaces and very simple paths in 3-dimensional space. And what we're seeing in this section of notes is their connection to defining them with the use of vectors. All right? And what we are setting ourselves up for is some of that furthering of our study of paths in three-dimensional space, the case for vector-valued functions, and the case for having surfaces in three-dimensional space, right? The case that we have here for planes. All right. With that said, I have, I think, one more video to present to you where we are going to go a little bit more complex in our surface descriptions that we can encounter in three-dimensional space and introduce ourselves to what's going to be known as the quadratic surface, right? Which is going to come in a variety of different forms. And to begin understanding those variety of different forms, what we're going to have to start to look at are the cross-sections of these surfaces, right? And what we're going to find for the cross-sections of these surfaces, they're going to take on shapes that are rather familiar to us by now. They're going to take on shapes, a lot of them take on shapes that are going to resemble conic sections, or they're all going to take on shapes that resemble conic sections when we look at their cross-sections, right? And we're going to see some of that conic section material come back into play to help us understand these quadratic surfaces. All right, so we are going to finish out with introducing ourselves to a few more descriptions of surfaces that can happen in three-dimensional space, ones beyond the plane, and you'll notice this is rather analogous to our understanding of lines in two dimensions. We started off very simply with looking at linear equations in two-dimensional space, and then we moved off into what? We took our line and we gave a curve to it. And when we take a line and we curve it once in space, we typically encounter a quadratic equation. Well, we're doing the same here with surfaces, right? We're going to consider taking a planar surface and starting to put some curvature into that planar surface. And the first cases for curvature that we're going to encounter when we curve, right, our space in three dimensions, a planar surface in the three dimensions, is we are going to encounter what we call the quadratic surfaces. All right, so that is the next section, folks. That is where we're heading, and that is where we're going to finish up this semester. So we are right there on the cusp of finishing. I hope you're hanging in there, and I'll see you in the next video.